Alrighty, so this is our chapter 20, radioactivity and nuclear chemistry. My name is Hope.
My name is Matthew.
My name is Alyssa.
My name is Mary Angela.
So the first topic that we're going to be discussing is electrons, protons, and neutrons. Those are the atoms containing those three primary particles. Your nucleus is a small, dense, positive charge ranging in the center of the atom. It contains the protons, which are positively charged, and neutrons, which are uncharged particles. Then we have electrons that are negatively charged particles located outside the atom, outside of the nucleus of the atom. They move very rapidly in very large volumes, while the nucleus is small and usually dense. Protons and electrons have charges that are equal but opposite in sign. So a neutral atom could have like a no charge electron. For example, an electron is usually a -1 charge with a mass in AMU of 5.486 times 10 to the -4. And a proton with a positive is usually a mass in AMU of 1.007. Neutron with a 0 charge is 1.009 mass AMU. Then you also have what's called isotopes. Isotopes are atoms of the same elements that have different mass. So sometimes they contain the same number of protons but contain different number of neutrons. For isotopic calculations, you would have to look at the periodic table essentially. So if you have something, for example, as far as chlorine, the atomic number would be 17 and the given mass number would be 35.45. That's based on the... No, it's still there. It's not going to shut off. The atomic mass, the weight average of the mass of an isotope that makes up chlorine. Chlorine consists of chlorine 35 and chlorine 37, which is a ratio of 3:1. A weighted average is an average corrected by the relative amount of each isotope present in nature. When you're determining atomic mass, you have to first convert the percentage to a decimal fraction. Then you have to multiply the decimal fraction by the mass of the isotope to determine the contribution of each isotope. Then you have to add the mass contribution for each isotope. Finally, an example that was given in our notes was neon. So neon 20 is a mass of 20 AMUs with and that's basically atomic mass.
Okay, and then nuclear radiation is energy given out spontaneously from the nucleus of an atom. And the atoms that do this are called radioisotopes. And most of them occur naturally, but mostly in elements that have atomic numbers of 83 and higher. And the several types of nuclear radiation are alpha particles that consist of 2 protons and 2 neutrons and carry a +2 charge. And they're large and don't travel far. And then there's beta particles that are high energy electrons that are produced when a neutron turns into a proton. And they're more penetrating than alpha radiation, but can still be stopped by certain materials. And then gamma radiation is pure high energy electromagnetic radiation that has no mass or charge. So it can penetrate deep into different materials in the body. And then other emissions include positrons, which are positively charged particles with the same mass as beta particles, and neutrons that have no charge and can be used to trigger nuclear reactions. And radiation can ionize atoms in living cells, which can damage tissues and DNA and lead to health effects, negative health effects. And so people working around radioactive materials use protective equipment and exposure badges to track how much radiation they receive.
Then we talked about radioactivities and radioisotope. Then we talked about a table that shows depends on what type of radiation you're exposed to, what do you need to protect yourself. For example, if you have the alpha, you only need paper, clothing, or if you have beta, you need foil, plastic, or glove to protect yourself. Then we talked about how much radiation is too much. We give the unit of the radiation, which is SV, and then the average yearly dose that we get exposed to. Then we talked about radiation sickness. We said that it depends on the time and the dose, and then that sometimes when it is a short, intense dose, it could be very harmful to us. We talked about how much exposition could like get symptoms. For example, if you have 5,000 to 20,000 MREM, we're gonna have no symptoms, and if we have 300,000 to 400,000, we're gonna start having symptoms, and we could die in 30 days. Then we talked about equation, the nuclear equation and radioactive decay. We said that the rules are mass numbers must balance, atomic numbers must balance, and element change when proton number change. We also talked about how to write a decay equation, where we said that we write the isotope first, then we add the emitted particle on product side, and then we solve for the missing isotope by balancing mass plus atomic number.
An example of like radiation that occurs in like society today would be stuff like fMRI or radiation from chemotherapy. Those are modern day examples of radiation exposure that we have on a daily basis. And that's it.
Still gonna go, yeah.
Go.
Alright,
Sorry.
no, it's good. Finally, we learned about like radiation units to determine like disintegration, and we used the Curie and the Becquerel, and then we learned about half-lives, which is like how long concentration can go before it loses like 50% of its concentration, and we were given the formula and the chart to determine that. And then finally, we went over, as you said, like medical applications for radioisotopes. So like she said, like fMRI, X-rays. There's also like high energy rays from like more like, you know, complicated like machines and stuff. So yeah, basically they use a safe amount of radiation without putting like patients in danger, and they use it to destroy stuff like thyroid cancer, and yeah, they also have radiation therapy, but you know, they do that safely. So
Thank you. That's our
Thank
chapter
you.
20.